Right, so for phases of the moon, we actually already talked about this to some extent as well. If we have the sun coming in from the left here, what we see, of course, is a full moon when the moon's on the opposite side of the Earth and the sun, and then actually start with a new moon, and the moon's on the same side as the sun. Now, if we get a new moon during eclipse season, then we're going to actually get a solar eclipse, but that's relatively rare. And as we swing around, we get into a first quarter moon. As seen from the Earth, the first quarter moon here is going to appear basically half lit and half dark. And notice it's the right side that's lit and the left side that's dark. So if we look down at, imagine looking at the moon here from the Earth, we're going to see the right side lit and the left side dark. So that's the first quarter moon. And then we swing around to a full moon, and then a third quarter moon is exactly the opposite of the first quarter. The left side's lit, the right side's dark, and then we move into new moon again. All right, it's pretty much already covered this, just the idea that we have to have the precise alignment between the Earth, Moon, and the Sun, so we have to be along the line of nodes, we have to have the Earth on the line of nodes, and then actually have, for instance here, a new moon, in order to get a solar eclipse. This is a nice shot taken by, it's actually taken by a unmanned spacecraft, and we have it closest and looking back. And it's not a composite, it's not a Photoshop, not what we call a tabloid photo. This is an actual photo of the moon and the Earth, and you can actually get an idea of what the relative sizes really are, because what we're seeing here is the moon is about roughly 25% the size of the Earth, and obviously the sun is to the right there, so we're seeing the size of both objects there. This is a shot taken from Skylab, which is a now burned up, very early days orbiting astrophysics lab that was in orbit around the Earth. And what this is actually the shadow of the Earth during a solar eclipse, or solar eclipse. So this is actually the umbra that we spoke of earlier. That's the deepest part of the shadow where you would not see any part of the sun at all. And as you move out, you can start to see the gray and of the penumbra there. And then farther out, these folks are not seeing that eclipse at all. And the Skylab astronomers are actually able to watch the spot move from west to east across the U.S. as the basically due to the orbital motion of the moon dragging its shadow along during the solar eclipse. All right. Well, again, I probably don't want to spend too much time on this. Just the same idea. Because of the tilt of the two planes, we're only going to actually get eclipses when we have eclipse season, when the Earth is actually on this line of nodes. And again, the line of nodes is the line of intersection of those two planes. So out here, this is not eclipse season because the Earth is not on that line. And so if we get a new or full moon here, we're actually not going to get any eclipses in that case. Any eclipses fairly hard. Okay. Tidal locking is something a little bit new here. We're going to talk about that. All right, well, we've already talked a little about tides in connection with a hydrological cycle on the Earth. You know, we talked about how there's 2 low tides and 2 high tides every day, every 24 hours. Well, that's actually, of course, due to the gravitational effect of the moon. But there's also a counter effect that the Earth is performing on the moon, which is also a tidal effect. But in this case, what we're seeing is that it's actually a much stronger effect. The Earth's effect on the moon is much stronger than the moon's effect on the Earth when you look at this tidal effect. And there's a couple of reasons why that's true. But that effect of the tidal force is actually the reason that the moon keeps the same phase pointing towards the Earth at all times. I think I mentioned already that the Earth's spin is gradually slowing down right now because of the tidal effect of the moon on the Earth. And eventually, I'm talking like 1 trillion years from now, the Earth is actually going to keep showing the same face toward the moon all the time. But when you reverse the two actors in this thing, and you talk about the Earth's effect on the moon, that's so much stronger that we actually already have what we call a tidally locked orbit. This is our first example of a synchronous orbit. There's many examples in the solar system of what we call synchronous orbits, where different time scales have become related to each other in a way that becomes a physical lock. The simplest one is tidal locking, which is exactly what we have in the case of the Earth's orbit around the moon. Tidal locking. So that what's happened is it's a synchronous orbit in the sense that the spin period of the moon, its actual spin period, is exactly equal to its orbital period. So if you think about it, it's not that the moon is not spinning. It's just not spinning relative to the Earth, right? But it is spinning. If you keep your eye on this big crater here, it's obviously pointing to the right there, now it's up, now it's to the left, now it's down there. So it's actually, in the frame of view of the distant stars, the moon actually is spinning. But its spin period is exactly equal to its orbital period, and so that's what we call tidal locking, and that's why we have the moon always keeping the same face toward the Earth. All right, so just to get into a little bit more of this, and of course the detailed math, including the derivations from the calculus, will be on the third exam, because I know you guys want to be challenged. That's okay, no problem with that. I keep getting all these anonymous emails from people calling for more calculus, more trigonometry, so, you know, try to be responsive to what people want. Well, it all starts with Newton's law of gravity here, which is basically the simplest form right there that we've seen before. Now, we're talking about the force that this is actually the force that the moon is exerting on the Earth. This is the regular tidal force of the moon on the Earth. It's going to be the gravitational constant times the mass of the Earth there times the mass of the moon divided by the distance between the 2 points squared. And what we basically find is that, of course, the far side of the Earth has a weaker force acting on it than the near side of the Earth does. It's indicated by the length of these arrows here. There's a much stronger force that the moon is exerting on the Earth on the near side than on the far side, and this leads to the kind of stretching phenomenon that creates the tidal bulges that we see on the Earth. But exactly the same thing is also happening with the moon acting, the Earth acting on the moon. Okay? So what we're going to do is real quick look at that formula. Just one other point I could make about this. So you notice that we're interested in the difference between forces on two sides of the Earth here. Again, this is the force that the moon is acting on the Earth with. So if we think about the difference between two forces on the near side and far side of the Earth, then in a sense we're talking about kind of the change in the force as we move across the Earth. Well, that's, in calculus, that would be considered a derivative, rate of change. So that's why we see this funny looking thing up here. It's actually the derivative of the normal Newtonian force. So it has that funny form. But notice that it has the cube of the distance in the denominator, not the squaring. All right, so that's why these formulas now have the cube of the distance there. So what we have here is two forces written down. The first one is the tidal force of the moon acting on the Earth. Okay, so that's the one that we just saw in the last panel. That's the one that creates the tides on the Earth. But we can write down a formula, just the same kind of formula, with just a couple of small changes, which gives us the force that the Earth is acting on the moon with. All right? And if you compare these two formulas, they're actually very, very similar. The distance there is the same, because it's the same distance between the Earth and the moon, no matter how you look at it. The gravitational constant is the same. The two masses are the same, the Earth and the moon. These factors here are a little bit different because this is always going to be the radius of the object that's being acted on. And the reason that's there is because we're talking about the difference in force across that object. So a larger object like the Earth is going to have a larger change in force across it than what we're going to have for the moon. All right, so what this means is that because the Earth is about 4 times larger in radius than the moon is, that actually means that the force that the moon is exerting on the Earth is actually about 4 times larger than the force that the moon is experiencing due to the Earth. So on the face of it, that looks like the tidal effect is larger acting on the Earth than it is acting on the moon. It seems paradoxical because I just said that the Earth is still spinning and the moon is showing the same face toward the Earth. So it seems to kind of contradict that because it's saying that the tidal effect on the Earth is 4 times stronger than the tidal effect acting on the moon. But this is only part of the picture, because remember, this is the force that's acting on the body, but it's not the whole picture, because we also really are interested in how the body is reacting to that force. So we have to think about the other part of Newton's laws, which is basically the F equals ma part. So the force acting on the Earth is 4 times larger than the force acting on the moon. But the Earth is 80 times more massive than the moon. Okay? So even though the Earth is experiencing a force that's 4 times larger, it's 80 times more massive. So with this F equals ma idea, its acceleration is much, much, much smaller. So if you do the math, you have a force that's 4 times stronger, but the mass is 80 times larger. So what that means is in net terms, we have the force or actually kind of the acceleration that the moon experiences, the tidal acceleration is 20 times larger than the tidal acceleration that the Earth feels. Okay? And that's really the bottom line, because the acceleration is the way the mass is reacting to the force. That's really going to give you things like tides and accelerations and different types of motions. All right, so the bottom line here is that basically because the Earth is coming from masses on the moon, its tidal effect on the moon is 20 times stronger than the reverse tidal effect. So if we now reverse the picture here, the moon, if it were still spinning with respect to the Earth, it would have tidal bulges, just like the Earth has tidal bulges. But think about the difference though. The difference is that the moon doesn't have any water, right? So if the moon were to be spinning, now we're looking down from the North Celestial Pole here, so this is Santa's alternate workshop when things get too busy. Normal workshop moves here on the moon. But if the moon were spinning with respect to the Earth, we would have this counterclockwise spin. And then the bulges always have to point towards and away from the Earth, but these are bulges in rock now. So as the moon spins, its rock is deforming, and different parts of its rocky body are getting distended here and compressed and expanded. So what that basically means is that a lot of the moon's spin energy would be converted into heat, because all this stretching and crunching of rock, of course, is going to take some of that spin energy and convert it into heat. And once you do that, you don't get the energy back. So it's actually what we call a form of dissipation. So the moon's spin energy is actually gradually dissipating. Well, it's all gone now, but over the billions of years, it gradually dissipated through heating of the lunar crust. And you might think, okay, well, if all this, deformation was going on the moon, maybe it would be molten or something from all this heat. Well, there really wasn't that strong a form of heating. It was just a kind of gentle heating of the crust, and that heat was just simply radiated away into space. So what we have now is a moon that shows the same face towards the Earth at all times, and is very cool. It's not hot or anything. Its spin energy has basically all been radiated away. And the same thing is happening to the Earth right now, but it's going to take 1 trillion years for the process to complete on the Earth, so it's just slowly happening. Now, there is another aspect to this, which is that another quantity here called angular momentum can't be created or destroyed. It can't change form either, unlike energy. Energy can be dissipated into heat or something like that. But angular momentum is a special quantity that has to always be conserved. So if you think about what's happening as the Earth slows down, it's losing what we call angular momentum, which is the momentum of a spinning motion. But it can't really go, it can't just disappear. So that angular momentum, which is going away from the Earth, has to go somewhere. It actually ends up being transferred into the moon's own orbit. So what happens is that as the Earth slows down, the moon picks up angular momentum and is gradually moving away from the Earth at a ridiculously slow rate of only 1 or 2 centimeters per year. And eventually, about 1 trillion years from now, it will have reached a significantly larger distance of about 550,000 kilometers there. So it's going to increase its distance from the Earth by about a factor of 50% or so compared to current conditions. And at that time in the future, the Earth and the Moon will always show the same faces towards each other forevermore. And it will actually be kind of a doubly tightly locked orbit, if you will. Both bodies in the orbit will be tightly locked to each other at that point, and they'll just be staring each other down for the next, eternity.